Engineers analyze the requirements and specifications, taking into consideration factors such as weight, load capacity, and aerodynamics. They use advanced software and simulations to create designs that meet the necessary standards and regulations. Through controlled heating and cooling processes, annealing and quenching, the material properties are optimized to ensure high strength and resistance to fatigue. These treatments involve subjecting the landing gear components to specific temperature ranges and carefully controlling the cooling rates to achieve the desired results. Sophisticated and digitalized industrial processes are then employed for manufacturing the landing gear components. Computer numerical control (CNC) machines are used to shape and form the various parts with utmost precision and accuracy. Surface treatments and painting are crucial steps in landing gear manufacturing. To guarantee the highest quality, the landing gear undergoes the latest generation quality checks. Once all the landing gear components are ready, the assembly process takes place. State-of-the-art assembly lines are utilized to bring together the various parts efficiently. Finally, extensive in-house testing capabilities are employed to evaluate the performance of the landing gear. Rigorous tests are conducted to simulate various operating conditions, including extreme temperatures, vibration, and load scenarios. Consisting of a machine steel hub to which the axles and wheels are attached, the landing gear meets extremely precise and demanding specifications. The landing gear of the world's largest commercial aircraft, A350, must be able to withstand a weight of nearly 570 tons at takeoff and more than 390 tons on landing. Safran Landing Systems is a world leader in aircraft landing and braking functions.
The assembly begins with extensive design and planning. Engineers and designers collaborate to create detailed blueprints and 3D models of the helicopter. These designs must meet stringent safety standards and performance specifications, tailored to the specific requirements of different models, such as the light single-engine H125 for civilian use or the heavy twin-turbine H225 for more demanding applications. The next phase involves the manufacturing of individual components. This stage is critical as each part must adhere to high-quality standards. Components such as the fuselage, rotor blades, engines, and avionics are produced either in-house or sourced from specialized suppliers. For instance, the fuselage, often made from lightweight yet durable materials like composite fibers and aluminum alloys, is crafted to ensure both strength and aerodynamic efficiency. Once the components are ready, they move to the sub-assembly phase. Here, smaller parts and systems are assembled into larger sections, such as the tail boom, main rotor assembly, and cockpit. Technicians fit the avionics, electrical wiring, and hydraulic systems during this phase. Each sub-assembly is rigorously tested to verify functionality and integration. The primary assembly occurs in a specially designed assembly line. Sub-assemblies are brought together in a carefully sequenced process. The fuselage is mounted and the rotor system is installed, followed by the integration of the engines and avionics. The assembly line utilizes both manual labor and robotic systems to ensure precision. Skilled technicians and engineers work collaboratively, ensuring each step meets Airbus's strict quality control standards. Testing and quality assurance. After the main assembly, the helicopter undergoes extensive testing. Static tests check the integrity and safety of structural components, while dynamic tests evaluate the performance of moving parts such as the rotor blades and engine systems. Flight simulations and ground runs are conducted to assess the helicopter's operational capabilities. These tests are crucial for identifying any issues that need addressing before the helicopter's first flight. Final assembly line, FAL, and customization. In the FAL, the helicopter receives its final touches and customizations based on customer requirements. This can include specialized equipment for law enforcement, medical evacuation configurations, or military modifications. Each helicopter is tailored to meet the specific needs of its end user, ensuring it can perform optimally in its intended environment. The E-175E2 boasts impressive weight and payload capabilities. It has a maximum takeoff weight, MTOW, of 44,600 kilograms, 98,120 lb, and a maximum landing weight of 40,000 kilograms, 88,184 pounds. The aircraft can handle a maximum payload of 10,600 kilograms, 23,368 pounds, allowing for flexible operations, whether carrying passengers, cargo, or a combination of both. Fuel efficiency is a critical aspect of its design, with a maximum usable fuel capacity of 8,522 kilograms, 18,787 pounds, ensuring the aircraft can operate efficiently over a range of distances. Seating configurations. The E-175E2 is versatile in its seating configurations, catering to various airline requirements. 3-class configuration. This layout accommodates 80 passengers, with 12 seats offering a generous 36-inch pitch, another 12 seats at a 34-inch pitch, and the remaining 56 seats at a 30-inch pitch. This configuration is ideal for airlines aiming to provide a mix of premium and economy seating. Single-class configurations. The E-175E2 can be configured for higher density seating. One option seats 88 passengers with 80 seats at a 31-inch pitch and 8 seats at a 30-inch pitch. Another high-density layout seats 90 passengers with 42 seats at a 30-inch pitch and 48 seats at a 29-inch pitch. These configurations are suitable for airlines focusing on maximizing passenger capacity on regional routes. Performance. The Embraer E-175E2 excels in performance, combining speed, range, and operational flexibility. Max cruise speed. The aircraft can cruise at a maximum speed of Mach 0.82, allowing for swift travel between destinations. Field length requirements. The E-175E2 has 2 takeoff field length metrics: 1,730 meters, 5,676 feet under standard conditions, and 1,370 meters, 4,495 feet under certain operational scenarios. Its landing field length requirement is 1,345 meters, 4,413 feet, making it capable of operating at airports with shorter runways. Service ceiling. With a service ceiling of 41,000 feet, the E-175E2 can fly at high altitudes, benefiting from favorable wind patterns and avoiding congested lower airspace. Range. The aircraft has a range of 2,000 nautical miles, 3,704 kilometers, making it suitable for various regional routes, including transcontinental flights within larger landmasses. The Falcon 8X offers unparalleled customization options thanks to its extended cabin, providing various configurations to suit individual preferences and needs. This flexibility allows for a comfortable 3-lounge setup with an aft shower, ideal for relaxation and convenience. Alternatively, the standard entryway can be chosen to expand lounge space, creating a more open and spacious environment. For extended journeys, the option to include a larger entryway with lie-flat crew quarters or a grand galley ensures that both comfort and functionality are maximized. The cabin size of the Falcon 8X further enhances its appeal. With an internal height of 74 inches and a width of 92 inches, the spacious interior ensures ample room for movement and comfort. The cabin length of 42 feet 8 inches provides a substantial area for personalized configurations and luxury fittings. Additionally, the cabin volume stands at 1,695 cubic feet, offering significant space for a variety of uses. Complementing this is a baggage volume of 140 cubic feet, ensuring that ample storage is available for all travel needs. These features make the Falcon 8X not only a versatile choice for business and personal travel, but also a canvas for owners to tailor the aircraft to their unique tastes and requirements. The Boeing 787-9, affectionately known as the Dreamliner, is a marvel of modern aviation. Introduced to the KLM fleet in 2015, this aircraft has revolutionized long-haul travel with its fuel efficiency and advanced engineering. Capable of flying up to 8,500 nautical miles, the 787-9 can easily cover extensive routes, such as from New York City to Bangkok. Passengers traveling to destinations like Delhi, Mumbai, Rio de Janeiro, Bogotá, Cartagena, or Salt Lake City might find themselves aboard this state-of-the-art aircraft, although specific routes may vary by season. The Dreamliner earned its nickname from a global competition held by Boeing in 2003. This aircraft is celebrated not only for its long-range capabilities, but also for its environmental efficiency. The 787-9 is constructed using a blend of materials: 50% composite, 20% aluminum, 15% titanium, 10% steel, and 5% other materials. This composition makes the aircraft lighter and more fuel efficient, reducing waste and chemical use compared to similar aircraft. The focus on sustainability extends to its recyclability, further underscoring its environmental benefits. Each Boeing 787-9 in the KLM fleet is named after a flower, a charming tradition that personalizes the fleet. The first Dreamliner was named Sunflower, followed by others like Carnation, Lavender, Bougainvillea, Dahlia, Mimosa, Jasmine, Morning Star, Tulip, and Orchid. These names evoke a sense of beauty and serenity, much like the experience intended for passengers aboard these aircraft. The interior of the 787-9 is designed with passenger comfort in mind. KLM's interactive seat map allows travelers to explore the seating layout and select their preferred seats before boarding. This bird's-eye view of the aircraft helps passengers plan their journey for maximum comfort, ensuring a pleasant start to their trip. The Boeing 747-8 is the final model in the iconic 747 family, representing Boeing's largest aircraft. Introduced on November 14, 2005, as a response to the Airbus A380, it offers two main variants: the 747-8 TEF Freighter and the 747-8 Thai Intercontinental. The freighter had its maiden flight on February 8, 2010, followed by the passenger version on March 20, 2011. The cargo model was delivered in October 2011, with the passenger variant entering service in June 2012. This aircraft features an 18-foot, 5.5-meter fuselage stretch, bringing its total length to 250 feet, 76 meters, making it the longest airliner until the 777X's debut in 2020. The 747-8's wings are redesigned to be thicker, deeper, and wider, equipped with raked wingtips for improved fuel efficiency. These changes help it accommodate more fuel and reduce drag, enhancing overall performance. The aircraft is powered by General Electric GEnx engines, adapted from the 787 Dreamliner, making it more efficient than its predecessors. Its maximum takeoff weight, MTOW, reaches 975,000 pounds, 442 metric tons, making it the heaviest Boeing aircraft. The freighter variant can transport up to 308,000 pounds, 140 metric tons, over 4,120 nautical miles, 7,630 kilometers, while the Intercontinental can carry 467 passengers in a typical 3-class configuration over 7,790 nautical miles, 14,430 kilometers. 155 units of the 747-8 were produced, including 107 freighters and 48 passenger versions. The final aircraft, a 747-8F, was delivered to Atlas Air on January 31, 2023. This model exemplifies advancements in aerodynamics and technology, retaining the iconic 747 silhouette while integrating modern efficiencies, making it a remarkable chapter in Boeing's aviation legacy.
The process begins with the defueling of the aircraft to ensure worker safety and prevent the risk of fire or explosion. Once the fuel is drained, fuel-related components such as fuel lines from the tank to the engine are removed. The F-16, a highly versatile fighter aircraft, is renowned for its agility, speed, and advanced capabilities. It features a single-engine, multi-role design and is equipped with advanced avionics and weaponry. Next, the bolts that secure the wings to the aircraft fuselage are opened. There are a total of 16 bolts, 8 on the top and 8 on the bottom, which are loosened using specialized tools. After the old wings are removed, other components on the wings are also taken out for future aircraft assembly. The old wings are carefully packaged in a large crate for transportation to the repair facility. The F-16 has been utilized by numerous air forces worldwide, serving in various missions, including air superiority, ground attack, and reconnaissance. Its exceptional performance and reliability have made it a staple in modern military aviation. The new wings are then hoisted onto the aircraft using a crane. Alignment pins are used to ensure precise alignment of the wings. Once the new wings are in position, the bolts and brackets are tightened using anti-vibration sealant. This prevents direct contact between the wings and the fuselage, minimizing the risk of damage from vibrations or ground movement. One crucial component is the forward fuselage, which is responsible for housing the cockpit and critical avionics systems. The wingspan of the F-35 measures approximately 10.6 meters, 35 feet, providing a wide surface area of 42.7 square meters, 459.6 square feet. These specifications ensure optimal lift and maneuverability while accommodating various weapon systems. Once the major components, including the forward fuselage and wings, are complete, the electronic mate and alignment system come into play. This system ensures that the electrical and avionics systems within the aircraft are properly integrated and aligned. The F-35 incorporates stealth technology to avoid detection by radar. Some improvements include durable and low-maintenance stealth capabilities, integrated radar and sensor systems, high-speed data networking, and low life cycle costs. It also utilizes helmet-mounted display technology instead of the traditional head-up display. The F-35 is equipped with electronic systems such as the AN/APG-81 Active Electronically Scanned Array (AESA) radar, and the Electro-Optical Targeting System (EOTS), mounted under the aircraft's nose, designed by Lockheed Martin and BAE. The Gripen is a light single-engine multi-role fighter aircraft with a length of 15 meters, a wingspan of 9 meters, and a maximum takeoff weight of 16,500 kilograms. It can achieve a maximum speed of Mach 2 at high altitudes and 1,400 kilometers per hour at low altitudes. The aircraft features 10 pylon stations that allow it to carry reconnaissance pods, weapons, and external fuel tanks. One notable feature of the Gripen is its quick turnaround time. In air-to-air configuration, it takes only 10 minutes, and in air-to-ground combat configuration with weapons, it takes 20 minutes. The Gripen's internal fuel tanks have a combined capacity of 3-4 tons, which is approximately 40% larger than the previous version. This increased volume was made possible by moving the landing gear from the fuselage to the inner wings. The Gripen has a digital cockpit with 3 large multifunctional displays, including a few 3D screens. It also features a The Gripen is a light single-engine multi-role fighter aircraft with a length of 15 meters, a wingspan of 9 meters, and a maximum takeoff weight of 16,500 kilograms. It can achieve a maximum speed of Mach 2 at high altitudes and 1,400 kilometers per hour at low altitudes. The aircraft features 10 pylon stations that allow it to carry reconnaissance pods, weapons, and external fuel tanks. One notable feature of the Gripen is its quick turnaround time. In air-to-air configuration, it takes only 10 minutes, and in air-to-ground combat configuration with weapons, it takes 20 minutes. The Gripen's internal fuel tanks have a combined capacity of 3-4 tons, which is approximately 40% larger than the previous version. This increased volume was made possible by moving the landing gear from the fuselage to the inner wings. The Gripen has a digital cockpit with 3 large multifunctional displays, including a few 3D screens. It also features a Gripen is an aircraft that is compatible with various types of weapons, excluding the Mauser BK-27 27mm cannon. It can carry air-to-air missiles like the AIM-9 Sidewinder, air-to-ground missiles like the AGM-65 Maverick, and anti-ship missiles like the RBS-15. Through the MS-19 upgrade process in 2010, Gripen became compatible with a range of different weapons, including the long-range MBDA Meteor missile, short-range IRIS-T missile, and laser-guided GBU-49 bombs. During flight, Gripen has the capability to carry up to 6,500 kilograms, 14,330 lb, of weapons and equipment. It is equipped with external sensor devices for reconnaissance and target designation, such as the Rafael Lightning Targeting Pod, Saab's Modular Reconnaissance Pod, or Thales Digital Joint Reconnaissance Pod. Gripen also features advanced integrated electronic warfare capabilities, including the ability to passively detect and actively jam enemy radars, as well as a passive missile approach warning system to detect and track incoming missiles. Saab supplies the Active Bright Cloud electronic countermeasure system developed by Celix S. Additionally, Gripen is equipped with an enhanced survivability technology module, a self-protection compartment designed to counter missile threats. Submarines have long been a symbol of naval innovation, combining cutting-edge technology with strategic prowess beneath the world's oceans. Among the most recent additions to this elite club is the S-81 submarine, a remarkable achievement in Spanish naval engineering. This article explores the fascinating details and technological advancements that define the 81 submarine, known as the Isaac Perel, highlighting its significance not only for Spain but also for global naval operations. The genesis of the S-81 submarine dates back to the early 2000s, when the Spanish government approved a plan to modernize its naval fleet, including the replacement of its aging S-70 class submarines. The new submarine was envisioned to possess state-of-the-art technology, improved stealth capabilities, enhanced combat systems, and extended operational range. Air-independent propulsion, AIP system. One of the most noteworthy features of the S-81 submarine is its air-independent propulsion, AIP system. Unlike conventional diesel-electric submarines, which rely on atmospheric oxygen to operate their diesel engines, the AIP system allows the S-81 to stay submerged for longer durations, minimizing the need to surface and thus reducing its vulnerability to detection. This remarkable technology significantly enhances the submarine's stealth capabilities and extends its operational range. Enhanced sensors and sonar systems. The S-81 submarine boasts a sophisticated suite of sensors and sonar systems that enable it to detect, track, and engage both surface and underwater targets with unmatched precision. Its advanced sonar capabilities make it a formidable asset for anti-submarine warfare and intelligence-gathering missions. Silent propulsion. Silent propulsion is a critical aspect of submarine design, and the S-81 excels in this regard. Its advanced electric propulsion system minimizes noise, making it extremely difficult for adversaries to detect whether they are surface vessels or other submarines. This stealthiness gives the S-81 a strategic advantage in covert operations and surveillance missions. Modular design. The S-81's modular design allows for flexibility in its mission capabilities. It can be adapted for various roles, including anti-submarine warfare, intelligence gathering, special operations support, and mine warfare. This adaptability ensures that the submarine remains a versatile asset in Spain's naval arsenal. Improved habitability. Submariners often spend extended periods beneath the ocean's surface, making comfort and habitability vital. The S-81 submarine incorporates modern ergonomic designs and improved living conditions, ensuring the well-being of its crew during prolonged deployments. The commissioning of the S-81 submarine, named after the Spanish engineer and submarine pioneer Isaac Peral, has far-reaching implications for both Spain and international naval operations. Enhanced national security. The S-81 strengthens Spain's national security by bolstering its maritime capabilities and providing a powerful deterrent against potential threats. With its advanced technology and stealth capabilities, the submarine significantly contributes to the country's defense posture. Global strategic reach. The S-81's extended operational range and adaptability make it a valuable asset for international naval operations. Spain can contribute to allied missions, such as anti-piracy operations, intelligence gathering, and humanitarian assistance, while enhancing its standing in the international community. Technological collaboration. The development of the S-81 submarine represents a collaborative effort between Spanish shipbuilder NAVA-NTIA and various international partners. This cooperation not only showcases Spain's technological prowess, but also strengthens diplomatic ties and international defense partnerships. Economic impact. The construction and maintenance of the S-81 submarines provide a significant economic boost to the region of Cartagena, where the NAVA-NTIA shipyard is located. This project generates jobs, stimulates local economies, and supports the growth of the Spanish defense industry. While the S-81 submarine represents a remarkable achievement in naval technology, it also faces challenges and considerations for the future. Cost and maintenance. High-tech submarines like the S-81 come with substantial costs, both in terms of initial construction and ongoing maintenance. Spain must allocate resources effectively to ensure the long-term operational readiness of its submarine fleet. Emerging threats. As technology evolves, so do the threats faced by submarines. Spain must continually invest in research and development to stay ahead of potential adversaries and adapt the S-81's capabilities to meet evolving challenges.
The construction and float out of the HMS Prince of Wales, a majestic aircraft carrier of the Royal Navy, marked a significant milestone in the modernization of the British naval fleet. This engineering marvel, which began its construction in 2011, culminated in a spectacular float-out event in December 2017. The HMS Prince of Wales, the second ship of the Queen Elizabeth-class aircraft carriers, was built at the Rosyth Dockyard in Scotland, a historic site renowned for its shipbuilding heritage. The construction process was an intricate and well-coordinated effort that spanned several years. The vessel's journey from a collection of steel plates to a fully operational aircraft carrier was documented through a mesmerizing time-lapse video. The construction of the HMS Prince of Wales was an impressive feat of engineering. It required meticulous planning, precision, and the efforts of thousands of skilled workers, engineers, and project managers. The ship's frame began to take shape in 2011 when the first steel was cut. Over the next 6 years, the dockyard buzzed with activity as sections of the carrier were constructed in massive dry docks. The time-lapse video of the construction provides a captivating visual journey through this process. It starts with the assembly of the carrier's keel, the backbone of the ship. The keel was laid with great precision, and then, like a complex puzzle, the various sections of the vessel were assembled around it. Gigantic cranes and specialized equipment were used to carefully lift and position each section into place. The time-lapse footage captures the gradual growth of the ship, from the initial skeleton to a massive and imposing structure. The intricate network of pipes, wires, and compartments necessary for the ship's operation is meticulously integrated into the carrier's design, from the engines and propulsion systems to the flight deck and living quarters for the crew. Every aspect is constructed with precision and care. The HMS Prince of Wales is equipped with state-of-the-art radar systems, communication equipment, and weapons systems. These components were carefully installed and tested to ensure the ship's readiness for its future role in defending the United Kingdom's interests. Finally, the culmination of this remarkable construction project was the float-out ceremony that took place in December 2017. The float-out marked the moment when the HMS Prince of Wales was launched into the water for the first time. It was a monumental occasion attended by dignitaries, naval officers, and shipyard workers. As the dry dock was gradually flooded, the enormous carrier began to rise, buoyed by the water. The sight of the HMS Prince of Wales gracefully floating on the surface of the water was a breathtaking spectacle. It was a testament to the skill and dedication of all those involved in its construction. The float-out event not only celebrated the completion of the construction phase, but also symbolized the beginning of a new era for the Royal Navy. The HMS Prince of Wales, along with its sister ship, the HMS Queen Elizabeth, represents a formidable addition to the British naval fleet. These aircraft carriers are capable of projecting power and influence on a global scale, ensuring the UK's continued ability to protect its interests and contribute to international security.
The repair and maintenance of a cruise ship like the MSC Magnifica is a complex and highly coordinated process. Cruise ships are not only large but also sophisticated vessels, requiring meticulous care and attention to ensure they remain safe, functional, and aesthetically pleasing. When the MSC Magnifica arrived at Damen Ship Repair Rotterdam in October 2014, it marked the beginning of a comprehensive repair and maintenance project. One of the first steps in repairing a cruise ship is to berth it in a dry dock. The MSC Magnifica was placed in Damen Shipyard's largest dry dock, which is an impressive 307 meters in length. Dry docks are like massive floating basins that can be drained of water to expose the ship's hull. This allows workers to access and inspect the ship's underwater components, including the hull, propellers, and rudders. Before any repairs begin, a thorough inspection and assessment of the ship's condition are carried out. This involves a team of experts, including marine engineers, naval architects, and divers, who inspect every aspect of the vessel, from the exterior hull to the interior machinery and systems. Any damages, wear and tear, or safety issues are documented. Repairing the hull is often a critical aspect of cruise ship maintenance. Any signs of corrosion, cracks, or damage to the hull are addressed. This can involve cutting out damaged sections and welding in new plates. Anti-fouling coatings may also be applied to prevent the growth of marine organisms on the hull. The MSC Magnifica, like all modern cruise ships, relies on a complex propulsion system, including engines, propellers, and thrusters. These systems are thoroughly inspected and repaired as needed to ensure optimal performance. Routine maintenance tasks, such as oil changes and valve adjustments, are also carried out. The ship's electrical and plumbing systems are inspected and repaired as necessary. This includes checking wiring, generators, and pumps to ensure they are in good working order. Upgrades may be made to improve energy efficiency and sustainability.